Good morning, everyone. My name is Jeff Basti, and today my thesis partner, Casmir Lesiewicz, will be presenting our thesis entitled A Hydrodynamic Analysis of Wavy Leading Edge Rudders. We would like to begin by thanking those who helped us throughout this project. Our advisor, Professor Adrian Onis, for his support and guidance through the design, construction, and testing of the rudders, as well as ensuring the setup would produce accurate PIV images. Our reader, Professor Elena Golubeva, and our editor, Professor John Lutz, for helping us to put our thesis into words. Pat Doherty for his assistance with the web's circulating water channel, and the team at Levision for guiding us through the setup and calibration of the PIV system. We'd also like to thank DiNapoli and Inc. for designing the software used in their 2020 thesis. I will begin by going over the theory and principles behind foils, as well as those specific to this thesis. I will then describe the background of this design and state the objective. Finally, I will describe the process in which we designed our rudder and constructed it before handing the presentation off to Casmir. He will discuss the testing procedure, results, and draw conclusions before making recommendations for future work. To discuss foil theory, we must first understand the geometric characteristics of a foil. The leading edge, as indicated by the red arrow, is the part of the foil which experiences the flow of fluid first. On the other end of the foil, as indicated by this red arrow, is the trailing edge. This part of the foil experiences the flow as it departs the body. We have U, the free stream velocity, L, the wingspan, C, the chord length, and ARG, which is the geometric aspect ratio and is the wingspan divided by the chord. Note that this foil has a finite span, unlike 2D foils, which are considered to have an infinite span as they extend the entirety of a testing apparatus. And lastly, the Reynolds number, which consists of the free stream velocity multiplied by the chord length and divided by nu, the kinematic viscosity. The Reynolds number is a non-dimensionalized ratio of inertial to viscous forces. There are two forces present when working with foils: lift and drag. To understand these forces, we must discuss what the angle of attack is. Alpha is the angle present between the chord line and the direction of the free stream velocity. Lift is the force perpendicular to this free stream velocity. Lift can be characterized by the non-dimensionalized lift coefficient, for which the formula can be seen on the right, and is lift divided by the density, free stream velocity, span, and chord length. In symmetric foils, to achieve lift, there must be a non-zero angle of attack. Drag is the force parallel to the free stream velocity and can be characterized by the drag coefficient, the formula for which can also be seen on the right. Another non-dimensionalized coefficient used when evaluating lifting bodies is the pressure coefficient. The pressure coefficient can be calculated along the body of a foil using the equation on the left, and is characterized by using the velocities u, the free stream, and v, the tangential. The graph from X-foil on the right depicts the pressure coefficient values along the body of a foil when the angle of attack is at 10 degrees. The yellow line on top of the foil relates to the yellow graph above the axis. This area of the flow was considered for this thesis as it was analyzed using the PIV images. This will be discussed more in depth later in this presentation as part of the validation study we performed. The boundary layer is a thin flow region that occurs next to a body. The no-slip condition states that the fluid directly adjacent to the surface does not move relative to the surface. This creates a velocity profile, as shown in the figure, between the surface and the free stream velocity. Boundary layers often begin laminar and transition to turbulent as the Reynolds number increases. A turbulent boundary layer tends to stay attached to a body better. This image demonstrates how flow separation progresses along the body of a foil. This occurs when the boundary layer is no longer able to follow the surface. When this happens, the lower portion of the velocity profile changes direction. As the angle of attack increases, the separation point will move toward the leading edge of the foil. Stall is characterized by a loss of lift and a significant increase in drag. Several characteristics influence the separation of flow, such as the foil shape and aspect ratio. An infinite or 2D foil will stall earlier than a finite or 3D foil. A higher aspect ratio will improve the lift to drag ratio, but will decrease the angle at which stall occurs. On ships, rudders are required to be designed so that the stall angle is greater than 35 degrees. This foil has a low angle of attack. Looking at the trailing edge, the wake region is quite small. In this portion, the angle of attack has been increased. Therefore, the wake region is moving farther up along the chord of the foil. And finally, the point of separation has moved far enough forward that the foil is experiencing complete stall. There are ways to delay the occurrence of stall. The method of achieving this goal in this thesis was by implementing a tubercle-like design on the foil. Now, you may be wondering, what is this so-called tubercle? Well, it is a point on the rudder that juts out of the leading edge, as indicated by this red arrow. This tubercle creates counter-rotating symmetric streamwise vortices that reintroduce momentum into the boundary layer here. This essentially adds energy to the boundary layer so that it can stay attached to the foil at higher angles of attack. The added energy increases the stall angle, which can increase the maximum lift created by the rudder and improve overall steering capability. Alternatively, the aspect ratio can be increased to improve the lift to drag ratio while keeping the stall angle constant. The tubercles can also reduce cavitation on the rudder surface to minimize damage. The concept of the wavy leading edge was inspired by the flipper of a humpback whale. These ridges, as indicated by the red arrow, are the tubercles. Fish and Battle investigated humpback whale flippers at the Westchester University, where they cut a flipper into 71 sections. They found that the cross sections closely match a traditional foil shape and use a similar NACA section to analyze the tubercles. Before this, some theorized that the purpose of the tubercles was to decrease drag by reducing tip bleed. This turned out not to be the case. This paper proposed that they were to delay stall at high angles of attack. Humpback whales rely on maneuverability to hunt, and their high aspect ratio flippers help them to achieve this. This comes at the cost of potentially stalling at lower angles of attack, leading to the need for tubercles. Fish and Battle were able to confirm that the tubercles generate vortices, but did not determine their effects on lift or drag. In this paper, Lee et al. Conducted CFD on foils with and without tubercles to determine their effects. They used a CFD simulation to model stall and cavitation. Figure 11 shows the results of one of their simulations. In this image, the gradients represent the pressure surrounding the foil, and the white area depicts the region in which cavitation was experienced. They did in fact see a reduction in cavitation with the addition of tubercles. They also observed that the tubercles create symmetric streamwise vortices, which help to delay the separation of the boundary layer. However, they also saw a reduction in performance in the pre-stall region. In this case, they used an asymmetric foil section and relied solely on simulation. More recently, this paper by Wrench, Gergel, and Nielsen conducted CFD simulations specifically on rudders with and without tubercles. They observed similar results, but only placed the tubercles on specific portions of the leading edge. Some locations aimed at delaying stall, while others hoped to avoid ventilation. They also analyzed the effects of parameters like amplitude and wavelength and established optimal ratios. This brings us to the objective of this thesis, which is to determine whether a wavy leading edge rudder improves hydrodynamic performance when compared to a conventional leading edge rudder using particle image velocimetry. A NACA 0018 foil was chosen for this thesis as it was used in the KCS model container ship and other series. It is a symmetric foil, meaning it is symmetrically mirrored across the chord. When positioned at an angle of attack of 0, only drag will be present, no lift, as was mentioned earlier. This foil has a maximum thickness of 18% of its chord length and an aspect ratio of 1.55. This was chosen as the limiting factor is the span. Therefore, the aspect ratio was set lower to extend the chord. The base model for the wavy leading edge was also a NACA 0018. This span of the rudder was chosen to be 252 millimeters or 10 inches. This was the largest size rudder that would fit in the apparatus without experiencing flow interference with the apparatus itself. A wave was developed on the leading edge of the foil using the characteristics of a wavelength of 25 millimeters and a wave height of 8 millimeters. The wavelength is 10% of the chord, and the wave height is 3% of the chord. These factors were chosen based on the geometry used in similar studies. The rudder was modeled using Rhino 3D along with the Rhino plugin called Grasshopper, which assisted in the creation of the sinusoid along the tip of the leading edge. A numerical slider was then used to modify the wavelength and amplitude of the sine wave. This made for easy manipulation of the leading edge. There were also some considerations made when developing the rudder. It had to have an easily interchangeable leading edge so that the conventional and wavy edge could be tested using the same trailing edge. Future designs could be optimized and printed more quickly since the entire foil does not have to be reprinted. The joint was developed around the shaft so that the apparatus would not have to be taken apart when exchanging the leading edge. The foil had to be strong so that it could withstand the forces induced by the flow. This was kept in mind when developing the joint. The foil was then 3D printed using PETG filament, which does not degrade in water and is generally considered stronger when compared to other filaments. I would now like to invite Casmir up to present on particle image velocimetry.
Thank you, Jeff. Particle image velocimetry, or PIV, is a method used to obtain the velocity field in a fluid. The figure shows a typical PIV setup. Seed particles are introduced into the flow and are illuminated by a laser. These particles are neutrally buoyant glass spheres and are so small that they look like a powder. The cameras take one picture, wait a set amount of time, and then take a second photograph. The program then analyzes the two pictures and tracks the particles between them. This means that the program is able to measure the distance and direction the individual particles traveled. Because we also know the time between the images, the velocities can be determined, allowing for the creation of a velocity field. Stereo PIV involves the use of two cameras in order to produce three-dimensional velocity components. Because the cameras view the area of interest from an angle, they're able to observe movement in the out-of-plane direction. An example of SPIV results is shown on the right. The size of the arrows is based on the magnitude of the velocity, and the color scheme is based on vorticity. As you can see, the result is a two-dimensional plane with three-dimensional velocities. We chose to use SPIV because of the ability to see these out-of-plane velocities. We hope that we might be able to observe the vortices created by the wavy leading edge. For our test, the cameras are arranged so that they are looking upwards from below the flow channel testing section, as shown in Figure 22. A wooden box is used to support the cameras and provide clearance for the cables. The laser is positioned next to the testing section so that the laser sheet is parallel to the ground. This orients the cameras perpendicular to the laser sheet. The plane of interest effectively takes a cross-section of the rudder. From this perspective, it's easy to observe the wake region, which is of the most interest to us. After getting the PIV system up and running again, the first step was to calibrate. The calibration is what is used as a reference to determine distances and directions. It also allows for the correction of refraction and warping due to the glass of the flow channel, the acrylic of our testing apparatus, and the water within the flow channel. A standardized calibration plate is located in the same plane and location as the laser sheet. In the past, the plate had always been held vertically, which made it easier to support. A new assembly had to be constructed in order to support the calibration plate horizontally. The calibration plate and assembly placed in the circulating water channel during calibration is shown in the figure on the right. A level was used to ensure that both the laser and calibration plate were level. Once the cameras are focused on the correct region, they take a photograph. In the post-processing program, Thesis 10, the calibration plate used is selected. Thesis then automatically maps the markings on the plate. The result is shown on Figure 24. Markings are a known size, shape, and distance apart, so they can be used for a reference for all of the following images. Before testing the models, we had to confirm that the PIV was providing accurate results. The easiest way to do this was to observe the flow channel without the apparatus and model. The flow should be parallel, and we should observe the expected speeds. The figure on the right is an example of one of our free stream velocity field results. As you can see, the flow is uniform. The speed was also close to the expected value based on data from the pitot tube. This does not necessarily validate all of our results, but acts more as a form of sanity check. The apparatus and model were then able to be installed. As shown in the figure to the right, the rudder is attached to a vertical shaft, which is supported by our acrylic testing apparatus. The angle of attack was varied between 0 and 50 degrees at a 10-degree interval. A second round of testing was conducted with a 25-degree angle of attack. This was done to observe an additional angle of attack closer to the stall angle. 5 speeds were tested, which produced Reynolds numbers between 3.08 times 10 to the 4th and 1.1 times 10 to the 5th. Each rudder was tested at every speed and angle of attack, starting with the lowest speed and 0-degree angle of attack. At each condition, a set of 100 image pairs were recorded with a delta T of 1,000 microseconds. This is the time between the first and second image in each image pair. It must be adjusted based on the velocities being observed. The particles need to travel far enough for the program to determine the distance and direction without traveling so far that they are impossible to track. The figure shows the laser being fired while recording one of the sets of images. Each set of images was processed in both 2D and 3D because the 2D view from one of the cameras proved to be the most effective for comparing the two rudders. To more effectively validate our results, pressure coefficients were calculated at 5 points between 10 and 50% of the chord. The locations of these points are shown in figure 28. The MATLAB script from DiNapoli and Ng's 2020 thesis was designed to perform these calculations and was modified to work for our data. This was done for 3 speeds and 3 angles of attack. X-foil was used to calculate the pressure coefficients at the same points for a NACA 0018 foil. X-foil is a 2D program, and we used a 3D foil, so there are 3D effects present that X-foil does not capture. However, the plane tested was distant from the ends of the foil, so the differences should be minimal. The pressure coefficients were plotted along with the values calculated in MATLAB. The resulting plot is shown on the right for 1 speed and angle of attack. The values closely match, indicating that the results are valid. An attempt was made to use their program to calculate the lift and drag as well, but the angle of the camera and the field of view prevented us from achieving reasonable results. Velocity fields for both the conventional and wavy models at the same angle of attack and Reynolds number are shown here. There appears to be a dramatic change in the size and shape of the wake region. The conventional leading edge wake boundary also appears to be smooth, while the wavy leading edge wake is less uniform. This is likely the result of vortices traveling downstream. The wake region is also much smaller, which seems to indicate that the wavy leading edge is effective. However, we still needed a way to quantify the difference. 2 metrics were established to do this. The first involved measuring the wake thickness. As you can see, the thickness of the wake is much smaller for the wavy leading edge in this condition. The second method involved measuring the point of separation, where separation began along the chord. However, the exact position along the chord is very difficult to determine because of the angle of the camera. Instead, the 2 images were aligned in AutoCAD, and the difference in the point of separation was measured relative to the edge of the field of view. Both of these metrics are a direct indication of drag. When considering the relation of wake thickness to the angle of attack, there was a clear trend. As the graph shows, the wavy leading edge appeared to be more effective at angles of attack closer to the stall angle. The graph plots the non-dimensionalized wake thickness against the angle of attack for 1 Reynolds number. It begins at a 25-degree angle of attack because separation has not yet occurred before this point. The wake thickness of the wavy leading edge rudder became closer to that of the conventional leading edge model as the angle of attack increased. This graph seeks to find a trend between the reduction in wake thickness and the Reynolds number. It plots the wake thickness of the wavy leading edge model as a percentage of the conventional leading edge wake thickness, with each line representing a different angle of attack. There did not appear to be any trend related to the Reynolds number. The 25, 30, and 40-degree angles do appear to show a somewhat similar trend, with the 25-degree angle having a much greater change in magnitude. However, the 50-degree angle of attack shows an inverse trend. This may be caused by the reduced effectiveness of the wavy leading edge at angles of attack further from the stall angle. Overall, there was a consistent decrease in the wake thickness of the wavy leading edge rudder when compared to the conventional leading edge. Moving on to the second metric, the change in the point of separation along the chord was plotted against the angle of attack. There did not appear to be any trend relating the point of separation to the angle of attack. The graphs for each Reynolds number also all had different patterns. This graph plots the percent change in point of separation along the chord against the Reynolds number. Each line represents a different angle of attack. There did not appear to be any linear trend, relating the point of separation to the speed. Each angle of attack seems to have its own pattern as well. Instead, the wavy leading edge consistently shifted the point of separation between 6 and 11% further along the chord. There was one value that fell outside of this range with an 18% shift further along the chord. This occurred at an angle of attack of 25 degrees and a Reynolds number of 1.1 times 10 to the fifth. When observing the velocity field, there is the most noticeable difference in the entire wake region at these conditions. It is possible that the wavy leading edge was able to reintroduce the most energy into the boundary layer at these conditions. In conclusion, the wavy leading edge consistently reduced wake thickness and pushed the point of separation further along the chord. This indicates a reduction in drag and delayed stall. In line with our objective, these factors demonstrate that a wavy leading edge rudder improves hydrodynamic performance when compared to a conventional leading edge at high angles of attack. This improvement seems to be the greatest at angles of attack closer to the stall angle and seems to be independent of Reynolds number over this range. However, this is only applicable to angles of attack at which separation has occurred. Within the pre-stall region, the velocity field appears to be very similar, but the effects on lift and drag are unknown. To further study the effects of wavy leading edge rudders, there are a few steps that could be taken. The first recommendation for future work involves varying the wavelength and amplitude of the wave used to create the wavy leading edge in order to find an optimal combination. Now that the wind tunnel is operational, tests could be conducted in the wind tunnel to measure lift and drag. Finally, purely 2D PIV could be conducted with the camera located directly below the foil. This perspective could lend itself to better use of DiNapoli and Ng's MATLAB program. It could then be used to calculate lift and drag based on the PIV data. Thank you for your time, and please hold any questions until after the remaining thesis presentations.